So we ended on Wednesday with the idea of a probability distribution. And I have random variables. In our case, we have discrete random variables. So there are a finite, countable number of outcomes. And then the probability distribution says, okay, here's my list of outcomes. Let's assign each one a probability. I did say that there were two rules required for a probability distribution. For each outcome, I need to know that the probability of that outcome is between 0 and 1, and that the total of all of my possible probabilities over all the i's that are allowed is exactly 1. So if we talk about flipping a coin, I have how many outcomes? Right. And I could label them anything I want. Heads and tails is perfectly acceptable. I could code them numerically, make it a 0 and a 1. But if I say, all right, flip a coin, I have outcomes, and then each outcome has a probability. If I assume that I have a fair coin, then ideally, each of these is a half. But it does not have to be a fair distribution. I could have a coin that's rigged slightly, right? It could be that maybe it's, 0.6 and 0.4. It could be anything. But does this follow both of the two rules that are listed there? Yeah. Each individual probability is a number between 0 and 1, and the total is exactly 1. There's a question in the text that says, here are my outcomes. And here is the probability of each of those outcomes. And it asks, is this a probability distribution? What do you got, Felix?
Yeah, it sounds up to 90.
Ah, crud. It satisfies the first condition. Each number is between 0 and 1, but 0.4 and 0.1 is 0.5, 0.75, 0.8, 0.95, it's less than 1. This is not a probability distribution. I'm going to make an abbreviation. Probability distribution function. PDF. You'll also sometimes hear this called a probability density function. So sometimes this word distribution is replaced by the word density. That shows up more often when instead of talking about discrete things, we talk about continuous things, which is next chapter. So we won't use that term, but I will slip occasionally and forget and just say density when I want you to see both names. Sometimes I don't have the PDF up front. I have to make it. My random variable is the number of heads I get when flipping a coin 3 times. Under the assumption it is the coin we were looking at earlier, which is fair. I don't know what the probability distribution looks like. So how do I find out? I need to write out.
So you write out the PDF, but you can flip the coin 3 times.
Yeah, but that only told me what happens that one time I flip it. How do I know how likely one event is over the other? Felix? I can make a tree diagram to list all the things that could happen and then go through and determine the probabilities for all of my possible results before I get that far. I'm flipping this coin 3 times. What are the possible things that could happen for my random variable x?
Yeah, 0, it's 1, twice, and 2 times in the same tails.
That's it. So my only options are 0, 1, 2, 3. Now I figure out how many times after I do 3 flips will each of those things occur. So to fill out this bottom row, I need to look at all the things that could happen. Felix, you suggested a tree diagram. So I think about this in time, like I flip the coin once, and it either comes up heads or tails. I flip the coin a second time, same thing. I flip the coin a third time, and that's all the possible things that could happen for my 3 coin flips. Now, starting at the root of my tree over there on the left, work your way to the right and write down a string of H's and T's for each branch. So if I follow this top branch up here, this branch right here, all 3 coins came up heads. The next branch, the last coin came up tails. The next branch down, the middle coin came up tails. And in the next branch down, both coin 2 and 3 came up tails. And I can go through and I can write all of these out. And now I have all the possibilities. All I have to do is count how many of these have no heads. Just 1 out of 8. Assuming the coin is fair, all of these are equally likely. All of these 8 possible outcomes. But these events up here are not equally likely. We just said there's 1 out of 8 ways there. But how about 1 head? There are 3 of those. Here, here, and here. Similarly for 2, and for 3. So I have my probability distribution. I should check. If you add those up, what do you get? 1. And each number is between 0 and 1. Perfect. So this is my PDF, my probability distribution function for 3 coins being flipped. There is another type of distribution where instead of using individual frequencies, we use cumulative behavior. So I'm going to take this same experiment, and instead of asking about what is the chance that I get exactly 1, what's the chance I get 1 or fewer, 2 or fewer? So if I, instead of writing my events and then the probability that I get exactly that item, this is a probability distribution. I'm going to say, oh, I'm going to give you a list of my xi's, and then I'm going to ask for the probability that we get less than or equal to that. For this experiment, we would have this. Because our PDF looked like that, right? So I'm basically saying, oh, to get 0 or fewer, to get 1 or fewer, to get 2 or fewer. So I'm summing up all the stuff up to, like our cumulative frequency distributions did when we were doing descriptive statistics. Because it's cumulative, this is called a CDF, a cumulative distribution function. Questions? Different types of random variables have different kinds of characteristics that will describe their probability density and their cumulative probability distribution and their cumulative distribution. So if I have something where I say I've got a mean and a standard deviation, that might tell me something about what the probabilities up here should look like. Or maybe I talk about the type of random variable. We were rolling a die, 1 die. All the probabilities were the same, right? But when I roll 2 dice, the probabilities start to change if I add the numbers. If I just look at the numbers, well, then the probabilities are all again the same, 1 out of 36 for each possible option. But depending on the variable itself, the x, I may or may not be able to get some information about what these numbers should look like and maybe an equation to govern them. That will be particularly useful. This particular PDF represents the number of patients who come into the emergency ward between midnight and 6 a.m. at a hospital. Who shows up to the emergency room? How many cases do we get? What is the chance it's going to be a busy night? With a PDF, I just have to count the cases and add them up. Bigger than or equal to 4 means it's equal to 4 or any number bigger than 4. All I have to do is add the two numbers. 0.15 plus 0.05 is 0.2. The chance that it is less than or equal to 3. There are two different ways to answer this question. One of which is shorter than the other.
Can count everything. That one for bigger than 4, so we could just subtract it from 1.
I know everything has to add up to 1. This is the complement of this. Complement's 1 minus. Oh, perfect. This is 1 minus the chance that it is bigger than 3, which is the same as bigger than or equal to 4. 1 minus 0.2 is 0.8. Ta-da! By the way, this equivalence is important. In this type of discrete random variable, saying bigger than 3 means bigger than or equal to 4. When I get to continuous, that's not the same thing. Again, I could use unions, the word or. I could use intersections, the words and. But if I've got discrete cases, you really can't do and, can you? Chance I'm going to have no people and 1 person? Not going to happen. But the chance I have 0 people or 1 person, 0 people or 2 people, excluding 1. That's just an or, and they're disjoint. So I just have to add them. There's no overlap. Questions? The chances of any given number of people occurring in the night shift here are not the same. How many people should I expect to show up? I can think of this distribution as if it was just a set of weighted statistics. Just a set of weighted numbers. I've heard that description before when I thought in physics terms in our descriptive statistics stuff. We thought of balancing things, right? We had weights at different points on our number line, then we said we could balance stuff. Well, if I think of having 0, 1, 2, 3, 4, 5, but I put different weights based on this, then I could find the balance point again. That's a mean. That's an average. And the best part about that is that the formula simply tells me to multiply the weight by the number and add them all up. We can only do this for numerical data. So where I did heads and tails, I wouldn't be able to give you an expected value. If I called heads a 1 and tails a 0, then maybe I could do an expected value, right? Here, I've got number of people. If that's the formula, add up for all the different values of I, add up the probability of each one times the number for each one. Well, here's the number for each one and the probability for each one. Let's do the expected value of number of cases in the ER overnight. I'm going to run out of room, so I'm going to put this underneath. The expected value for this variable is 0 times 0.05 plus 1 times the chance for 1, which was 0.3, plus 2 times the chance for 2, plus 3 times the chance for 3, plus 4 times the chance for 4. Oops, that's the wrong number. Write down the right number. Plus 5 times the chance for 5. We add it all up. What do you get? You add all this up. It's kind of hard to have a quarter of a person as a case, unless that's a really bad accident. So I would say we're more likely to get 2 than 3. But if we actually looked at this for several days running, we would say out of every 4 days, I'd get 1, 2, and 3 3s. That would balance it more towards the 2 end than the 3 end. Sorry, 3 2s, 1 3. If this is an average, what was my symbol for average? Mean, mu. We'll use the same symbol. And because this is a theoretical probability distribution, not an empirical one, I'm not using the X bar. This isn't a sample. This is the whole population. This is probability. This is over everything. There are dozens of applications here. I asked the other day who drives. If you drive, you have car insurance, right? Why? I'm a good driver. I don't need insurance. So, someone somewhere in an office says, Dr. Sassmore is a over 50 male with glasses, has 1 accident in the last 10 years, no speeding tickets in the last 10 years, no moving violations. People in this group with no violations in the last 10 years, with less than 2 accidents, they get this rate. Why?
Probability on whether they're going to have to pay you or not.
They've done the expected value. And if they charge me this much, and they only have to pay this many times, then I balance out. My expectation is that I will have enough money from all of the insurance rates that I've collected to pay the people I have to pay, including the payroll in my office. We did lottery tickets last week, right? Monday? I lost track of what day it was. We did lottery tickets. How much do you charge for a lottery ticket? You charge enough to cover the payout, right? If you charged $1 a ticket and there was a 2% chance of winning, and you were going to win $100, wait a minute. Let me write that one down. I like that example. Outcome, win, lose. If I win $100. If I lose $1. Charge me $1 for the ticket. And we said there was a 2% chance of winning. So what's the chance of losing? Ready? 100 times 0.02 plus -1 times 0.98. This is the expected outcome on this game, this raffle. What happens? Now remember, losing is negative, winning is positive. Should you play this game? You expect to come out $1 ahead. You absolutely should play this game as often as you can get away with it, because you're going to come out ahead more often than not. On the other hand, here's your lottery ticket. Your winning chance is 1 in 1,000. Prize is $100. What should you expect to have happen? By how much? Give me the expectation here. What is the expected value for this? Which is?
-0.899.
So if I'm the player, this is bad. But if I'm the house, I collect $1,000 for selling all the tickets, right? And then I only have to pay out $100. That's money to me. Every single game in a casino is set up this way on purpose. As a matter of fact, the expectation on a game in a casino is called the house edge. When you walk into the Rivers down in Pittsburgh, they'll have a bunch of slot machines, right? And above the slot machines, you'll see 99 slot machine or 98 slot machine. Do you know what that is? That's the expected value on $1 for them. They expect to pay out 1% less than they take in, or 2% less they take in. My favorite casino game is roulette. Anybody know roulette? Y'all are staring at me like maybe. Okay, roulette has a wheel. There are 38 numbers on the wheel, the numbers from 1 to 36, and then a 0 and a 00. The 0 and the 00 are green. 18 of the numbers are black. 18 of the numbers are red. You can bet all sorts of different ways. Roulette, you can bet on one number. You can bet on a whole stack of numbers. You bet on 4 of them or 12 of them or 6 of them, or there's a whole bunch of different ways to bet. You can bet on all the red numbers or all the black numbers or all the odd numbers or all the even numbers, except 0 and 0 don't, the 00 don't count in those behaviors. Let's make an easy bet. If I bet on red, I win $1 for every dollar I bet. By the way, I will get my original dollar back if I win. So I will be up a total of 2 if I win. I will be at 0 if I lose. But if these are my outcomes, what's the probability? If I'm betting on red, how many red numbers did I say there were? 18 out of, because the 0 and the 00 are on there. But the 0 and the 00 are green, not red. So I would lose on them. I'd also lose on all 18 of the black numbers. Wait a minute. That means the expected value for this behavior is 1 times 18 over 38 minus 1 over 20 times 20 over 38, because a loss is negative to me. That's negative 2 over 38. Somebody grab a calculator. Give me a decimal for negative 2 over 38.
Zero, 5, 3.
Or 0.53, you said. 5.3%, right? Every single bet on the roulette table has an expected value of negative 5.3%, except one. The crown bet on 0, 00, 1, 2, and 3. Its expected value is negative 7%. It's worse. It looks like such a fun, exciting game. For every $100 you play, you will lose 5 of them. On average. The casino makes $5 off of every $100 played at the roulette table. Regardless of whether you win or lose, they profit. Best way to make money in the casino? Own the place. Lotteries the same way. Games of chance. But in my opinion, the biggest use of this is still insurance payments and insurance rates. Should I buy this policy or not? As long as I know the probabilities of which way it's going to go. Questions? If I have a mean, I have variance and standard deviation. I'm going to use the same symbol, sigma squared. And we're going to sum up. Let's see. We took each value and subtracted the average. So I'm going to take each value and subtract the average. and I'm going to square that. And then we used to divide by either n or n plus, minus 1, depending on which way we were doing it. But since this is a probability, I'm going to do like I did up here in the expected value, and I'm going to multiply by the probabilities. The standard deviation is sigma. It's the square root of the variance. Now, I will be the first person to tell you that just like standard deviation for a descriptive statistics problem, doing this by hand's a pain in the ass. It's not impossible. It's not even all that long, but it certainly isn't a short process. Here, what is the chance of the number of rooms that get rented in February? I have to work out the average. They work it out right here. Then I take each of these numbers and subtract this average, square those, and then multiply by the probabilities originally. And there's my variance. This is not worth doing by hand. If you get stuck and the question asks, do the standard deviation or the variance on a probability distribution, we can go right to Excel and right to a graphing calculator. I'm not going to make you do this by hand. Is it worthwhile knowing what to do? Absolutely. But more often than not, what we're really looking at is the fact that these two numbers, mean and variance, or mean and standard deviation more often, tell me everything I want to know about the distribution itself. Having these numbers then allows me to determine what my distribution looks like. Or knowing something about the distribution gives me a nicer, easier formula for these. Questions? So what's an application of the standard deviation or the variance in some of the situations we were just talking about? Standard deviation measures kind of how wide things are, how far away from the average we get. That's what the subtracting of the average is doing for me. It's like range spread. So it could be that on some nights I get 5 people in the ER. We already decided that wasn't very likely. If I had a sudden run where 3 or 4 nights in a row, I had a lot of people in the ER, I might say, hey, something weird is going on. How likely is this? How unlikely is this? How far outside the norm am I? If I go to the casino and I watch the roulette wheel and it comes up red 7 times in a row, do I think there's something weird going on? Yeah, but not hugely weird. It's a random process. There's got to be a run of reds at some point. There's got to be a run of black at some point. If it's really unlucky, there'll be a run of greens at some point. But I just have to wait long enough to figure that out. The standard deviation, the bigger the standard deviation is, the more variability I have in how close to the mean I get. Questions? I have 2 very particular favorite distributions in this setting. One of them is called a uniform distribution. Okay, hang on a second. I hope it's self-evident from the name. What does it mean for a distribution to be uniform? So like my rolling one die, where all the outcomes have the same chance of happening, right? So suppose my random variable x covers all values from A to B inclusive, whole values only. Integers. So discrete, like we were just talking about. So all the numbers from A to B. 0, oh, we were just talking about the dice, right? 1, 2, 3, 4, 5, 6, my list. How many numbers are there from A to B? How many numbers are there from 1 to 37? Yes, that's a stupid sounding question. Just counting whole numbers from 1 to 37. There are 37 of them, right? Because it says inclusive. I include 1, I include 37, and I count tick, 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 all the way from one to the other. From 1 to 10. There are 10 of them. From 33 to 65. All right, wait a second. If I took away 33, then my list would start at 0, wouldn't it? 65, 33 to 65, subtract. Take away 30. What's 65 minus 33? You have calculators in front of you. You do not have to attempt to do arithmetic in your head.
What did you actually say?
65 minus 33. Good. But that would start at 0, wouldn't it? When we were counting, we started at 1. So add 1. 33 to 65. If you count them all out, including 33 and 65, you take the difference and add 1. So from 1 to 10, 10 minus 1 plus 1. 1 to 37, 37 minus 1 plus 1 gives me 37 again. 33 to 65, 65 minus 33 gives me 32. Add the 1 back on. Well, then, if that's how many there are, the probability of any one outcome is 1 over B minus A plus 1, so that they're all the same. That's what it means to be uniform. If there were 22 outcomes, each one has a chance of 1 in 22. And if I were to draw a histogram, it would look like that, where each of these were at a height of 1 over B minus A plus 1. And each of those marks is 1 unit apart. Well, now, let me think about this. I want to know the average. Isn't the average just in the middle of that? Each and every one of these values has the same probability. So I just have to add up all the numbers from here to here. And then I can figure out what the average is. Well, it turns out that the average is exactly in the middle. Right in the center. Wouldn't that be where you would balance that? Because it's a solid rod from one end to the other. Now, the variance calculation is long and ugly. So rather than actually work through it, I'm just going to give it to you. The standard deviation is if you want the variance, take away the square root. I promise the 12 didn't come out of thin air, but it's a little bit beyond where we are right at the moment. In other words, if I know where the list starts and where the list ends, I know everything there is to know about this distribution. I know what its shape is, I know what its average is, and I know what its spread is. Bottom of page 202. The required parameters are the lower and upper limits. The formula for my PDF, each one has the same probability. The cumulative distribution, we just count how many are below or equal to where we want to be and divide by the chance for each one. And there's my mean and standard deviation. There is a random command that allows me to generate, if I picked, what was it, 33 to 65, I could type rand between 33, 65, and Excel will spit out a random number between 33 and 65 for me, as many times as I want. Please notice, we were talking about our rolling a die. Left picture. Each bar is at exactly the same height. 1 out of 6. What's the decimal for 1 out of 6? Calculator's in front of you. What's the decimal for 1 out of 6? Notice we're just over 0.16 for a height. But if I start looking at the cumulative, 1 would give me 0.16, 2 would give me 1 or 2, so that's 0.16 times 2.33, then 0.5, then 0.667, and then 0.833, and then 1. And there's my cumulative distribution function. My cumulative distribution function is a straight line at an upward slope, whereas my PDF is flat. My CDF is always angled upward. Problem number 11. The ages of programmers at Synflex Corporation range from 20 to 60. If their ages are uniformly distributed, what is the mean and the standard deviation? Okay, wait a minute. The age goes from 20 to 60, inclusive. What's the average? Add the 2, divide by 2. Piece of cake. The standard deviation, unfortunately, requires me to chunk out that formula again. But the only 2 numbers I need are A and B. 20 and 60. Having this formula in front of me means I'm not going to do the long, big, arduous calculation. I'm just going to go right there and plug and chug. Which, by the way, if you do, should come out to be, I think, 11.8. Just under 12. And then we can ask questions like, what's the chance that if I pick somebody who's a Python programmer, that they're under the age of 30, or that they're over the age of 50. Over or equal to would be different, wouldn't it? So I can actually compute those probabilities once I have this idea in front of me. But I've hit the clock. I will talk about my other favorite distribution for this set when we get back from break. So I will see you all on Wednesday. You are reminded that the last chapter, chapter 5's assignments are due then. If you have questions, please feel free to email me. Otherwise, enjoy your fall break.